This presentation is going to cover the topic of frequency planning for RFSoC. To begin with, we'll define what frequency planning is and roughly what it entails. We'll then go into some of the reasons why we need to do frequency planning. In particular, the impact of non-linearities in the analog signal processing chain, which cause harmonics and intermodulation products. We'll also mention some of the other spurs which arise in the RF data converters themselves, in particular due to the phase lock loops that are used to generate the clocks. Finally, we'll look at a method of frequency planning, in other words, selecting parameters and frequencies carefully to avoid any of these unwanted spurs residing within the band of interest. So, what is frequency planning? Well, because the RFSoC supports such high sampling rates, then usually the sampling rate is much higher than the bandwidth of any communication system that we're likely to handle. We also recognise that there are some unavoidable artifacts which we'd prefer not to have overlapping with our signal of interest. Therefore, there's a motivation to do frequency planning. In other words, to make sure that none of these artifacts and degradations overlap with our desired signal. Any unwanted artifacts which are captured by the sampling process can later be removed or attenuated using filters. Having mentioned that some of the issues arise due to non-linearities in the analog signal processing chain, let's have a look at where that occurs, starting with the receive signal path. Notice that after the signal is captured by the antenna, it's quite small and therefore it needs to be boosted using an RF amplifier to scale it to approximately the range of the ADC input. This amplifier is inevitably non-linear to some extent, and as we'll see later, that's a source of imperfections. Looking now at the transmit side, an RF amplifier is required here as well. In this case, to boost the signal from the level output by the RF-DAC up to a much higher signal level that can be transmitted through the antenna. Once again, this RF amplifier is likely to be non-linear. Within the RFSoC device itself, the RF-ADC and RF-DAC blocks include internal buffer amplifiers. These are designed for high signal fidelity, and although their effects would be additional to those introduced from external amplifiers, it's expected that the external amplifiers would be the chief source of non-linearity in the system. Before moving on to look at some examples, let's just clarify what's meant by the term non-linearity in relation to amplifiers. A perfectly linear amplifier is shown in blue here. In this case, the output is a directly scaled version of the input. The scaling factor is constant across all input signal amplitudes. With a non-linear amplifier, which is shown here in red, that's not the case. The degree of gain varies according to the input signal amplitude. For values close to zero, the amplifiers behave in a similar way. But as the magnitude of the input signal increases, the non-linear amplifier deviates from the ideal. Mathematically, for a linear amplifier, the output Y can be expressed simply as AX, where X is the input signal and A is a constant gain value. However, for a non-linear amplifier, there are also some higher order terms. For example, with second and third order terms, the output Y is AX plus BX squared plus CX cubed. That means that additional components are generated that are not part of the original signal. In this example, we have a value of A is 10, B is negative 1.2, and C is 0.1. If we make the non-linearities even more severe so that we can easily visualize them in the time domain, then you can observe that the signal going in, which is a sine wave, is not a perfect sine wave at the output. In this example, the magenta signal at the top is the input to be amplified, and if we had a perfectly linear amplifier, we would achieve a higher amplitude sine wave as desired. At the bottom in red, we have the output of a non-linear amplifier, and you can clearly see that this is not a perfect sine wave. In other words, it includes a sine wave component at the correct frequency, but it also contains other sine wave components as well, and these are undesirable. Taking a simple example and looking at it in the frequency domain now, here we would like to amplify a sine wave at 62.5 Hz, which we'll refer to as the fundamental. In blue, we see the output of a linear amplifier. In this case, gain has been applied to the signal, but no other frequency components have been introduced, and this is the desired output. However, at the output of a non-linear amplifier, where we've considered second and third order terms, then you can see that in addition to the desired tone at 62.5 Hz, there are also some other components with significant energy. We have a second harmonic at 125 Hz, a third harmonic at 187.5 Hz, and there's also some other energy at DC, or 0 Hz. We can see a substantial difference between the perfect and non-linear amplifiers here. If we had used a more complex model for the amplifier, with fourth and fifth order terms for instance, then we would also see fourth and fifth harmonics appearing in the output of the non-linear amplifier. Thinking about the equation for the amplifier, we can analyse this to confirm the frequency of the second harmonic term. In this case, where the gain coefficient A is 10, and the second order coefficient B is minus 1.8, we derive that the additional output terms as a result of the second order term are minus 0.9, so that's a DC term, and a cosine term at twice the frequency of the input. Likewise, for the third harmonic term, we can work through some maths, which you can see the beginning of here, and ultimately we end up with two components, one at the frequency of the fundamental and a second at 3 times the frequency of the fundamental. Taking this output that arises from the third order term and adding it together with that from the second order term and also from the linear gain, we end up with this expression that you can see at the bottom. In other words, it contains a term at DC, or 0 Hz, a term at the fundamental frequency, another term at double the fundamental frequency, and a final term at 3 times the fundamental. If we wanted to also include higher order terms, the fourth and fifth harmonics and so on, then we could also derive those mathematically, although we won't do that here. It's worthwhile remembering that these harmonics arise from non-linear amplification, which is an analog process. Therefore, any harmonics that exist above half of the sampling frequency will be aliased as a result of the sampling process. In this simple example, where Fs is 1000 Hz, you can see that the fourth and fifth harmonics are above Fs over 2, and therefore these would alias. We can see the effect of aliasing more clearly if we redraw the spectrum using the limits of 0 to 500 Hz, or Fs over 2. Notice that the fourth and fifth harmonics have aliased here, and as a result, the fifth harmonic is actually situated quite close to the fundamental. If we wanted to extract the fundamental only and reject the harmonics, then we would actually require quite a tight bandpass filter here. You can perhaps also imagine a situation where the fifth harmonic, or one of the other harmonics for that matter, could end up extremely close to or overlapping the fundamental, and that would make it even more difficult. If considering higher order harmonics, for instance we've added the 6th, 7th and 8th order terms here, then these would also alias, in this case from the third nicosome. If all of these harmonics arose from an amplifier before an analog to digital converter, then if there was no analog filter to remove these terms, they would also alias. And as you can see, the spectrum is now quite cluttered with harmonics. So far, we've considered that the input to the amplifier was just a single sine wave. And clearly that's not realistic, because the signals that we transmit in practice will be composed of multiple frequency components. When multiple different frequency components are amplified, then we also have the problem of intermodulation between these terms. We'll start with a test of intermodulation where we input two frequencies F1 and F2, which are assumed to be quite close together. We will soon see the effect of intermodulation between these two terms, which is additional to the harmonics that we reviewed earlier on. For this section, we're going to go back to our simple model of the nonlinear amplifier, where we considered only the second and third order terms. Here, we've put in two frequencies that are close together, which we'll label FA and FB. Notice that the linear amplifier provides, as expected, these two tones without any other components being present. However, the nonlinear amplifier introduces quite a number of different components, and this set is composed of both harmonics, which we reviewed earlier, and also intermodulation products. We can now look at another version of this spectrum, with labels indicating what each of the different tones are. First of all, in dark blue, you can see FA and FB, and these are the two fundamental signals which were input to the amplifier. We also have a set of harmonics, which, as before, are integer multiples of each of the original frequencies. So we have tones at 2FA and 2FB, and those are the second harmonics, and then we have tones at 3FA and 3FB, which are the third harmonics. All of the pink labels represent intermodulation products. In total, we have 6 different intermodulation products, which are different combinations of FA and FB. If this signal was then to pass into an analog to digital converter, sampling at a frequency of 1 kHz, as we previously considered, then the uppermost 3 terms here would all alias down to sit below 500 Hz. In this figure, we've introduced labels to differentiate between second and third order intermodulation products. Notice that there are 2 third order intermodulation products labelled IM3, which are very close to the fundamentals FA and FB, and these can be particularly troublesome. It's very difficult to filter out unwanted components that are very close to the signal of interest, because a very sharp cutoff would be required. Measuring intermodulation in response to 2 test input tones is a common way of evaluating the linearity of components in a processing chain. The difference between the fundamentals and the resulting intermodulation products is expressed in dBc, or decibels with respect to the carrier. In this example, the power of the test tones is -5 dBm, and the measured power in the intermodulation products is -75 dBm, and therefore IM3 is measured as -70 dBc. Of course, in a communication system, the signals that we send will be band-limited signals, rather than 2 individual tones. This, therefore, creates a band of IM3 components, as opposed to 2 distinct tones. Once again, we can measure the difference between the input signal band and these intermodulation bands that are created. You can also notice that this band of IM3 products actually overlays onto the input signal band, which will cause some degradation to the signal. This concept of intermodulation products, and specifically IM3, is linked to the idea of adjacent channel leakage ratio, or ACLR, which is a standardized measurement used in radio standards such as 4G LTE and 5G. Energy spreads out from the main signal bandwidth into adjacent channels as a result, mostly, of IM3 intermodulation. Sometimes this is also referred to as spectral regrowth. The ACLR measurement quantifies the amount of power that leaks out into adjacent bands. Higher ACLR measurements in decibels are better, as this indicates a lower level of leakage into adjacent channels. Of course, when transmitting a communication signal, it's very important to minimize energy that's leaked into adjacent channels, as this can potentially affect other users of the radio spectrum. Over the next few slides, we'll have a look at some slightly more realistic examples based around the RFSoC and bands of transmitted signals. In this example, we've considered second and third order terms for our nonlinear amplifier. In green, you can see the signal of interest. This is a signal in the band from 400 to 500 MHz. Therefore, the center frequency is at 450 MHz and the bandwidth is 100 MHz. The center frequency of our harmonic band is twice the center frequency of the signal, at 900 MHz, and the bandwidth is now 200 MHz. Moving on now to the third harmonic band. This has a center frequency of 3 times 450 MHz, in other words 1.35 GHz, and the bandwidth this time is 300 MHz. Therefore, we can see that the center frequency of each harmonic is related to the center frequency of the signal by an integer value, and the bandwidth of each harmonic is also related to the bandwidth of the signal by the same integer value. Supposing now that our signal was at a higher center frequency, although still with a bandwidth of 100 MHz, then our second and third harmonics would be at 2 times and 3 times this center frequency. With a sampling frequency of 4 GHz, the third harmonic band would actually reside above Fs/2, between 2.1 and 2.4 GHz. This band would then be aliased and would be observed between 1.6 and 1.9 GHz. As you can see, it's adjacent to the second harmonic band here. Taking this example one step further, if the center frequency of the signal is even higher, then we might find that the second and third harmonics are both above Fs/2, and that both would alias back down into the region between 0 and half of the sampling frequency. In fact, depending on the values that we choose, we can end up with a situation where one or both of the harmonics are actually superimposed onto the signal. We see an example of that here. The signal is centered here at 1 GHz, meaning that the second harmonic is centered at 2 GHz, which is half of the sampling frequency, and then the third harmonic is centered at 3 GHz. The upper half of the second harmonic band is aliased down to sit on top of the lower half, but of more concern is the third harmonic band, which aliases down to be superimposed upon the signal. This would be highly undesirable because it would degrade the signal. With this example in mind, we can start to see the motivation for careful frequency planning. Choosing the sampling rates more carefully might have allowed us to manipulate the positions of the harmonic bands so that there was no superposition. Of course, harmonics can occur in response to other signals as well as our own signal of interest. As you can see in this example, there's an interferer centered at a frequency of 240 MHz with a bandwidth of 10 MHz. The third harmonic of this interferer partly overlaps our signal of interest. This could have been avoided by filtering out the interferer with an analog filter before it passed through the amplifier and had a chance to create these unwanted harmonics. In addition to the various harmonics and intermodulation products which arise from the amplifier, the RF-ADC and RF-DAC themselves contribute some imperfections. This arises due to the PLL or phase lock loop, which is used to derive the sampling clock, and there are also terms which are related to the sampling clock and the interleaving factor of the DAC or ADC. Looking specifically at the components derived from the phase lock loop, these appear above and below the bandpass signal of interest. For instance, if our signal of interest was 200 MHz wide and centered at 1 GHz, and the PLL mixing frequency was 400 MHz, then we would see two additional bands, one centered at 600 MHz and the second centered at 1.4 GHz. Based on our observations during this presentation, we have seen that several different factors contribute to produce harmonic bands, intermodulation bands, and various other bands related to the DAC and ADC. It would be ideal if we could come up with a frequency plan which would avoid any of these artifacts overlapping with our signal of interest. To that end, Xilinx provide an Excel-based frequency planning tool which helps the designer to work out optimal parameters. We've also made our own Python-based version of this tool, which is available on the web at the link provided here. The user can supply different parameters, immediately observe the resulting frequency plan, and make adjustments as required. In this presentation, we've discussed some of the analog effects arising from front-end amplifiers, which inevitably are not completely linear, although this can be minimized to some extent. The non-linearity causes harmonic and intermodulation products, which are undesirable artifacts, which are added to the signal of interest and can degrade it. In addition to this, other components also arise as a result of the sampling and PLL clocks, which are related to the RF-DACs and the ADCs. However, as the digital to analog interface of the RFSoC supports such huge bandwidths, much larger than most radio communication signals that we would encounter, then it's possible to undertake frequency planning to either avoid or minimize the superposition of these unwanted terms with the signal of interest. By frequency planning, we can carefully choose parameters which will avoid superposition. As we've seen latterly, frequency planning tools are available to help designers with this process. As a follow-up to this session, you may find it interesting to try out the frequency planning tool and make your own frequency plan for a given scenario.